Hello everyone. What you're looking at on the screen isn't just a collection of graphs, it's the pulse of my home. For over 2 years, I've had a dedicated IoT server running 24/7, quietly collecting and processing data from every corner of my house. As I talk, you will see the cycling of all my dashboards I built up using Grafana. I designed this specifically to take raw, invisible data and turn it into a real-time story of how my house is performing. My goal from the start was simple. I wanted a seamless way to deploy sensors, store years of history, and display the results exactly how I want to see them. To get this level of detail, I've built a custom ecosystem from the ground up. It starts at the edge with a fleet of ESP32 microcontrollers. For the technical-minded, these are low-powered Wi-Fi enabled nodes programmed via Platform I/O. They act as the eyes and ears of the system. For everyone else, these are tiny smart devices tucked away in different areas of my house, constantly sending updates over the air to my central Linux-based server, which is a Raspberry Pi 4. Whether it's temperature, humidity, furnace, hydrometer, current sensors, or the swimming pool temperature, every bit of data has a home. But a dashboard on a PC is only half the story. I also wanted to be able to monitor my home's vitals without having to sit down at a computer. In this video, I'm going to show you how it all connects, from the server backend to the battery-operated displays, including a cheap yellow display module I've built for at-a-glance monitoring. Let's dive into the hardware, beginning with the sensors that feed the system. I'll also show you how the battery-powered remote displays work and how they keep me updated without needing a PC. This is one part of a larger IoT ecosystem. If you'd like to see more of how-to behind the scenes, let me know and I'll break it down in a follow-up. Okay, this is one of my ESP32s. I think I have about over 10 of them around the house. There's 3 here on this bench in my workshop, and it's beside the furnace. In fact, the furnace is on, so this part of the video may be a little noisy. But this particular ESP, I've got it on a little breadboard, and it's connected to the furnace itself, in that these two are little 3.5 millimeter jacks, and they connect to the furnace plenum. One measures the heat coming into the furnace and one measures heat going out of the furnace. This pair of white wires, that is a signal that tells the board when the furnace is on. Now, the second thing is I wanted to measure airflow, and it was just easier to use another ESP rather than having to wire wrap something into the existing one. So this is a second ESP, and in this case it's wire wrapped to this breadboard because I wanted to verify the circuit first, because the way I measure airflow is I'm using an old computer fan, and I realize that with the taco pin, if I spin it with no power, it generates a waveform, and the peaks of those waveforms I can use to determine the rate of the airflow. And that's not calibrated airflow, so I just call it digital units. And if I'm getting a reading of so many digital units that shift suddenly, I can keep track of that because I graph them within the Grafana utility. So this circuit will create pulses from that varying amplitude sine wave, and then the pulses are simply measured by this ESP, and by measuring the time between the pulses I can calculate live power consumption of my house. The third board I have is this one here. This is the hydrometer, and this one has 2 wires here that go all the way to a black wire that actually goes outside to my hydrometer, and I have built up an infrared sensor, and it just sticks over the front of the hydrometer, the glass housing, right over top of where the IR LED is. All these meters have an IR LED that will produce a flash every time it measures 1 watt of electricity being consumed. Now you can check that by videoing it with your phone camera, because the IR will show up on the video of on the camera. So there, as I said, there are other sensors. There's ones that measure the power in my fuse panel using current traps, and environment sensors, and many others. Okay, this is my server rack, and on the server rack is where my IoT server is. And the IoT server is on this board. So this is a Raspberry Pi running Docker with a bunch of containers that provide the IoT services, such as Grafana or the MQTT protocol, which is what all the ESP32s around the house talk to. This here is a board that provides, acts as a UPS, which keeps the Raspberry Pi running in spite of power failures. So it has two 18650 cells, and I call it a UPS because unlike the traditional power packs, the traditional power packs, when you remove the power, they cut the power to the device you're feeding power to, which is not what I want. So then the other thing I did is I'm running the NUT UPS server, which is the common UPS monitor driver for Linux. And what I've done is I've used this Arduino Micro, and it's acting as a one of the common simple serial NUT drivers. So in other words, it emulates one of the common UPS NUT drivers serially, and therefore I can monitor the bus power going to the Raspberry Pi as well as the battery power, and I can feed on to the through serially to NUT. I can indicate when there's a power fail, and I can indicate when there's a low battery so that it will shut down gracefully. So now I want to talk about the monitor mode. It's a portable screen that allows me to monitor the information I'm interested in from my Grafana or IoT server database, because it does have Grafana, I mentioned earlier, but that relies on a computer. It must run on a desktop, and that's rather inconvenient, and that'll become apparent as I walk through the menus of the portable display. The first one I built is simply using a graphics display driver, the TFT ESPI, and that one is really running just in a basic text mode. Although it will do graphs, I record a history of both power consumption and the furnace. But then later on, I had built this one. Now this one is using the LVGL libraries. And then eventually I've now come to this one, which has a higher resolution. And it's all self-contained. In fact, what's nice about this is it's very quick to update. So if I go to here, it sort of snaps in place. Whereas if I go to this one, because it's a serial update, you can see it has to draw everything. So getting back to this one, that first screen is the environment screen, and I have 4 sensors, environment sensors. These are all ESP32s scattered around the house. 3 of the 4 are the newest BME 680, where it has the particulate measurement, the VOC, the CO2, and the IAC. While one of them, which is the third column over, which labeled out, it has just NA at the bottom three because it's the older version. I put that one up before the BME 680 became available. So it's been running outside probably 4 years. So that's this mode. Now it's getting its data from the IoT server because while the Grafana is a great tool for doing what ifs and such, it's not very portable because it has to run on a desktop. So this thing, if I go back to the main screen, I can now look at hydro. And all of these bits of data get updated once a minute. I don't want to overburden the IoT server because it's having to dig the updates out. And at the same time, it's getting data from the ESP32s. So in this one, you'll see two columns, fuse panel, hydrometer. The fuse panel, I actually put fuse clamps, current transformers on the panel. And I bring signals into an ESP32 with some little bit of electronics so that I can then measure the current. In fact, if you look at that, you can see phase 1 power, phase 2 power. I'm looking at the fuse panel column, the first one. And if you add those two numbers up, they should add up to 637. And then I got phase 1 and phase 2 power factor, as well as I'm measuring the voltage AC. In the second column is a hydrometer. This is the ESP32 board that I showed you earlier in this video, and that's counting the flashes on the hydrometer. So as you can see, the hydrometer is saying I'm using 639 watts, and my fuse panel meter is saying I'm using 641. So if I look at it on Grafana and lay the two on top of each other, they're almost a direct copy. They would be closer on this display if I were updating them at the same rates. And in the case of Grafana, I do that. If I look at the furnace, what you're seeing is the furnace is off, which is good because I'm in the furnace room and it's noisy. And I just display furnace on count for the day and a furnace off count for the day. And I use that to determine how long in the day the furnace has been on for. So in the lower right entry, it says 29%. That's as of right now. Later on at bedtime, we turn the thermostat back. So whatever that number is at, it will fall back quite a bit because for the next 3 or 4 hours until midnight, that average slowly starts to drop. Also, you can see the furnace in temperature. So it's coming in at 20.8 degrees and it's coming out at 24.3. Plus, I talked about that second board measuring airflow, and it's showing 6940 digital units. And it's within 40, 50, 60 digital units over time. And that's the low speed. The high speed is closer to 10,000. Now I've left the lower part blank because I'm thinking I will put in a graph to show me the furnace status over time, like I have on my first board. But and I'll show that later. So here, if I want to do power consumption, like I want to measure how much power something's using, this I'm getting data at I think it's a 2-second interval. So I auto scale this. I'm not sure if I'm happy the way it works. I may still change it. What I'm saying at the bottom is sum 2 is the difference in power at each sample. So if I turn on the old 60 watt incandescent bulbs, I will show pretty close to 60 watts. So that's a good way to go around the house and see what different items consume. And it's surprising, this doesn't it's not an onboard antenna inside, but it's one of those little bent metal antennas that is surprisingly sensitive. So I think it'll work, for example, if I want to go out and look at my pool pump. This is the graph one. And so this one is storing a graph horizontally. It stores about 2 hours of power consumption. And you see the min and the max. So the lowest it's been today is 186 watts, and the highest is 7.1 kilowatts. In fact, it's off scale. That's what those little green arrows say, that it's off scale. And I realize at some point while making changes, those lines on the graph should disappear. That's the green and the red line when it's off scale. Obviously, at some point, I messed that up. This will reset at the end of the day at midnight, along with other items. This is just a reboot button. If I need to reboot it, I use that mainly when I'm programming and I need to reboot it for some reason. And then finally, I have a little bit of diagnostics here. So if I'm having trouble, say I do go out to check the pool pump, it's winter right now, I haven't had a chance to try this outside, and I'm not sure I'm getting a good signal. I can look at the RSSI, and as long as it's above 80 dB, minus 80 dBm, generally I'll get a good, it will work properly. Now, something interesting is it amazes me how responsive the software is. So the reserve buttons I haven't defined, but I beep the reserve buttons, I beep when I press, and I beep when I release. So if you look and I do a rapid press, I'm really impressed with the response time. Anyway, that's my handheld graphical screen.